So today in this class I'm going to discuss about electric flask and Gauss theorem. I'll be asking you so many questions on this and Gauss theorem. Gauss theorem in electrostatics, okay? There are Gauss theorem in other fields also, and Gauss theorem. And after that, after some time we will learn that Gauss theorem is always applicable, but not always useful. Okay? It's always applicable. You can apply it anywhere, but not always useful because it has some limits, some conditions to follow. And then we have here electric flask. Okay, FLUS. Flask. In class 10 maybe you have heard about magnetic flux, electric flux, maybe I do not know, but let us try to understand the basics and the concept about this electric flask. Let me start with the area of plane figures. Plane figures. Plane figure means square, rectangle, trapezium, is it okay? Or a parallelogram and so on. We have so many plane figures. We also call them as 2D surface, right? 2D surface, two-dimensional surface, right? Plane figures, circle is also a 2D surface. Maths, we call it as 2D surface. In physics, we call it as open surface. Open surface. 2D surfaces are called open surface. Okay. And in physics, 3D surface. 3D surface. In maths, 3D surface means cone, cylinder, sphere. Is it okay? Cube, cuboid. These are 3D surface. In physics, we call it as closed surface. So this is going to play a very important role in electric flux and Gauss theorem. Is it okay? They are the hands and feet of electric flux and Gauss theorem. So let me ask a very small question. Is area a scalar quantity or a vector quantity? Is area of a square, area of a rectangle, area of circle, is it okay? Just think about any 2D surface, open surface. Then is area a scalar? Is area a scalar or a vector quantity? A scalar quantity. That's how you think. Okay, let me show you an example. Okay, let me show you an example. Suppose in this coordinate frame, the x-axis, the y-axis, and the z-axis. Okay, in this coordinate frame, I'm going to keep a square. I'm going to keep a square whose side is A. Whose side is A. Alright? Is it okay? So this square lies in xy plane, right? Having side A. Then the area of the square will be given by side square. Side into side, of course. Side into side. So side square. Side into side. So side square. That's how you have learned. But do you know actually how comes the area of a square is side square, or area of a rectangle is given by length into breadth? Actually, you see, area is not a scalar quantity, but the area is a vector quantity. Area is a vector quantity and it has always a direction. Is it okay? Area is a vector quantity and it always has a direction, so we call area vector. Area vector. Area vector. So area vector. Area has a vector quantity, so we call it as area vector. For this square, let me give the name of this square as ABCD. Okay, OABC. The name of this square is OABC. Then the area of, in this case, area of a square is given by the cross product of two adjacent sides of the square. Is it okay? So area vector is given by the cross product of two adjacent sides of the square. Correct? Now you see AB cross BC, cross product of two vectors is given by magnitude of AB times magnitude of BC with the sine of the angle in between them. See here, what is the angle between two adjacent sides of a square? 90 degree to sine 90 degree. Your magnitude of AB is small a. Magnitude of BC is small a again. Sine 90 degree is 1. So that gives you A square C. So area is a vector quantity and we call it as area vector. Is it okay? Now I'm going to ask you, what is the direction of this area? Thus, this square lies in xy plane. Then what is the direction of this area? The direction of this area will be in a direction perpendicular to the plane in which your figure lies. Your figure lies in xy plane. So the area will be directed towards the area will be directed towards the z-axis like this. If I direct one, your area lies in xy plane. So the area vector will be directed, okay, in a direction perpendicular. Your area will point in a direction perpendicular to the plane in which your figure lies. To ifalik tao po do, na? Arik tao do? Piche fali ina kao po do eh. Ino no hoy. See, z-axis to ifalik ta ze. Z-axis to ufalibik ta se do eh. Is it okay? Na? If your area vector is pointing in this direction, then it will be represented by unit vector k cap. Is it okay? And if your area vector is going in that direction, is given by this direction. If ito lang ang direction, this direction will be your k cap, and that direction will be your minus k cap. So in this case, your area vector can have two directions. One is k cap, or the other one is minus k cap. We know that unit vector k cap represents the direction of z-axis. So equal to positive z-axis, k cap equal to negative z-axis minus k cap. Are you getting me? Are you getting that? Yes. Now, why k cap or minus k cap? Why? Because if the cross product of any two vectors gives you a resultant vector, if R is given by the cross product of any two vectors, then this resultant should always be pointing in a direction perpendicular to both A and B. Is it okay? Now, if this is like a law from the vector, okay? If R is obtained by the cross product of two vectors A and B, then R will be pointing in a direction. R will always be in a direction perpendicular to the plane containing A and B. Is it okay? So we have the law here. Is it all right? Yes. The same thing I can give you some other examples. So you always remember, area is not only a scalar quantity, but area is is a vector quantity. Okay, and the area vector is obtained by the cross product of two adjacent sides, okay, of a square or for a rectangle. But what it is for a what in case of a circle then? Suppose this is your coordinate frame. This is your coordinate from the x-axis, the y-axis, the z-axis. This is your origin. Suppose I have placed this doesn't look good. Suppose I have placed suppose I have placed a rectangle in xz plane now. I have placed a rectangle in xz plane with length L and breadth B, with this side L and this side B. The measure of this side is L, the measure of this side is B. Is it okay? Then how will you find out the area? Area is a vector quantity, so area vector is given by the cross product of two adjacent sides of the rectangle, right? L cross B. So L cross B means L, magnitude of L times magnitude of B times sine of the angle between the two sides, which is 90 degrees. So that is equal to LB. What will be the direction? Here your rectangle lies in a direction, or here your rectangle lies in xz plane. So the area vector will be pointing towards the, acting towards the y-axis, like this. Your area vector, since your plane is like this, now, so either your area vector will be like this, or your area vector will be like this. Is it okay? So your area vector will be along j cap or minus j cap, where j cap represents the positive y-axis, minus j cap represents the negative y-axis. Are you following that? Yes. So that's area vector. Now, when you think about for a circle, okay, when you think about for a circle, we can just try for the circle as well. So this is your x-axis, this is your y-axis, this is your z-axis. Suppose your circle. Okay, your circle having the radius r lies in xz plane. Is it okay? So what will be the area vector here? What will be the area of the circle? Area vector means area of the circle with direction. Okay, area vector. So the area vector will be given by what? Will be given by, what is the area of the circle? Pi r square. Area of the circle is pi r square. Is it okay? Area of the circle is pi r square. And the area will be pointing in which direction? Yeah, the direction in which your area vector will be pointing is, if this is your circle is here in xz plane, so the area vector will be directed like this, or it will be directed like this. Is it okay? So the area always acts in a direction perpendicular to the plane containing the surface. Is it okay? Yes. Now, what about a 3D surface? 3D surface in physics we call it as closed surface. If we think about a closed surface, then let us consider a cuboid. We will consider a cuboid or a cube, okay, or anything. So Suppose you consider a cuboid. Yeah. See, this is a cuboid having how many faces? 6 faces. You want to find out the area vector of this face. You want to find out the area vector of this face. Right? Each face is in the shape of a rectangle, right? Okay. The surface of each face is a 2D surface, right? Okay. So you consider a 3D surface, a closed surface, and you want to find out the area vector of this surface here. Okay. So the area vector will be acting in a direction perpendicular to the plane containing this surface, right? That means your surface here ABCD, your surface here ABCD lies in which plane? Lies in which plane? It lies in XZ plane. So the area vector will be either acting in this direction, means in this direction perpendicular to XZ plane, means perpendicular to the surface, okay, but outwards, or perpendicular to the surface inwards. But for 3D surface, the area vector is always in a direction perpendicular to the plane containing the surface and acting outwards, not inwards. Inwards to normal. So here the area vector of this surface will be only positive of j cap. Will be only j cap, not minus j cap. If this was an open surface, only, then the area vector can have 2 directions. One is this direction towards j cap, and the other one is this direction minus j cap. Then the area vector would have been in this direction j cap, or it could have been in this direction minus j cap for an open surface. But for a closed surface, the area vector always acts perpendicularly outwards, normally outwards, okay, on the plane containing the surface, not inwards. Are you getting me? Similarly, can you tell me what is the area vector of this plane? What is the direction of the area of this face? Ito laga face laga. Yes. See? The area vector should always be in a direction perpendicularly outwards, right? Perpendicularly outwards to the plane containing the surface. Is it okay? Not inwards, right? Inwards na jabo do na, inwards na jabo, outwards si jabo. So the direction of this area will be minus j. Similarly, what about this surface? Similarly, you can calculate for this surface, all the 6 faces similarly. Is it okay? So for any 3D surface, you always need to remember that the area always acts in a direction. Area is always in a direction perpendicularly outward to the surface containing it. Is it okay? Yes. Now when we talk about a sphere, then, if you talk about a sphere, suppose a sphere has center O, right, having some radius maybe R. Where will the area act here? What will be the direction of the area? Radially outward. Yes, it should be in a direction perpendicular to the surface of this sphere. Suppose you consider a small element on the surface, right? Is it okay? And you want to find out the direction of the area of this part. Is it okay? this small element is a part of the surface of the sphere. Is it okay? The whole sphere can be, the entire sphere, the entire surface of the sphere can be assumed to be made up of these small elements. You add up all the small elements, that gives you the surface of the sphere, right? Okay. So now the area of this element will be directed radially outwards. But if you are drawing a perpendicular to the surface of any spherical object, then it should always pass through the center. At this point on the surface, you draw a perpendicular. Then you have to draw in such a way that it should always pass through the center. If you try to draw a perpendicular to the surface at this point, then it should always pass through the center. Is it okay? So this is how you represent the area vector of a 3D surface. In this case, a closed surface is your sphere. For a sphere, the area vector should always pass through the center. Is it okay? Yes, these are small things that you need to keep in mind before we discuss the electric flask. Is it okay? Are you clear with that? Okay. Now let us see what is electric flask. Electric flask means, you already know what is electric lines of force. Electric lines of force. So electric flask means number of electric lines of force, passing perpendicularly to the given surface. Suppose you have a surface. Kept in an electric field. How many electric lines of force are passing through this surface? How many electric lines of force, or how many electric field lines are passing through this surface perpendicularly? How many here? Three field lines are passing perpendicularly through the surface. Then in that case, your electric flask is 3. Electric flask is represented by phi and E. Phi E. Okay? Electric flux. So in this case, it is equal to 3. Is it okay? Now I'm going to tell you something here. How do you increase the electric flask? Suppose I want to increase the electric flask. How do you do? Of course, I'll give you the formula, okay? I'll give you the formula. I'll give whatever you need. But can you answer me that?
Increase area.
Oh, you increase in area. Okay, that is one thing. There is another reason. Yes. Why don't you increase the field lines? Why don't you increase the density of field lines? Because density of field lines gives the magnitude of electric. Is it okay? Oh, very good. So that means this electric flask is according to what? If you are saying this electric flask is directly proportional to the area, right? Huh? That means it's also direct, because as you increase the area, more field lines can pass perpendicular to the surface, right? Okay. And as you increase the density of the field lines, see, density of field line has increased. Density of the field lines gives the magnitude of the electric field. So as you increase the density of field lines, means you are increasing the magnitude of the electric field. Then your electric flux will increase. That means from the above two factors, phi of E, or you can just simply write phi, okay? Just simply write phi, no problem. Phi will be equal to A times C. But I'm going to write product of E and A. I'm going to write dot product of E and A. Dot product of E and A. Why? Why? Dot product of E and A means E A cos theta, right? Why dot product of E and A? Why not scalar product of E and A? Actually, this electric flux is a scalar quantity, okay? It's a scalar quantity. But it's given by the dot product of E and A means E A cos theta. Why should it be cos theta? Why cos theta is there? Why dot product? Because of this dot product cos theta is there, right? We could have simply written EA, finish, end game. No? But we are doing this cos theta. Why is that? Why is that? Okay. Okay. Let's see. Let's get you straight away with that. I've considered one such area. Is it okay? Let's see what is the area vector. What is the area vector of this surface? Itu surface laga area vector, no. This area is like this. This area is like this. Itu area tu kina rase? This area is like this. Okay, very thin area. This area, no? This area I have drawn like this on the board. Okay. Then what will be the direction of its area? Yeah, its direction will be. Okay, this will be the direction of the area, right? Okay. All right. I'm going to draw the electric field like this, or the field line, the electric field line crosses like this, making an angle theta with your area vector. Then what will be your flux? According to the definition, electric flux means number of electric field lines passing perpendicularly through the surface. Now, looking at this example, can you tell me, like, what is the electric flux here? What is the electric flux? Calculate electric flux. Then, can you see any electric field lines passing through the surface perpendicularly? See, perpendicularly means it should go in the direction of area, right? Because for any surface, area vector is always perpendicular to the surface, right? I don't know it. So that means this electric field line should pass in a direction of A, your area A, right? Now you see, this field line E is not passing normally to the surface, but its component is passing perpendicular to the surface. One of its component is going in the direction of area. Resolution of vectors. This E has two components. One is E will have two components, right? Yeah, E cos theta along this A. No? So along this area A, the component of E will be E cos theta. And perpendicular to this E cos theta, you have another component of E known as A sin theta. You see. Is it alright? So the component E cos theta of this E is passing perpendicular to the surface. So I can write AE cos theta, EA cos theta. See. For that reason, electric flux is given by the dot product of E. For that reason. Is it alright? Yes. So what is electric flux? The number of electric lines of force passing perpendicularly to the surface, or passing perpendicular to the surface, is known as your electric flux. Okay? And electric flux denoted by phi, or you can write phi E, which is given by E dot A, which is equal to EA cos of theta. Alright, that is all you need to know here. Okay. Alright. Now what I'm going to do is I'm going to draw a surface like this. Okay, let me draw a surface. I'm going to draw a surface like this. So this is your surface, a surface. If this is your surface, okay, let me draw according to your dimensional coordinate. Let me draw according to the coordinate frame now. Then that will be easier for you, right? Yeah. Suppose this is your surface. Is it okay? This is your surface. Okay, let me make it more easy for you. Let me make it more easy for you. Just like the previous case, I'm going to draw like this. Okay, I'm very poor in figures now. That's the problem. Yeah. Suppose this is a surface. This is your area vector. This is the area. Okay, the area is directed perpendicularly outwards, right? Okay. And then this is your electric this is your electric field. This is your electric lines of force. Your electric lines of force are in a direction along the area vector. Okay, is it okay? So many, okay, there are so many, I cannot draw all of them. Calculate the electric flux using the formula. You know the formula, right? No? So calculate the electric flux using the formula. What do you see? What will be the electric flux using the formula? See? Your electric field lines, no? And area vector, are they in the same direction? So what will be the angle between them? What will be the angle between them? E and A are in the same direction, so the angle between them will be 0. The angle between them will be 0, so your total electric flux will be given by E times A times cos of 0 degree. So that is E. Is it okay? Scalar product of only E, finish. Now suppose again the same thing. Your area is acting in this direction. Area is in this direction. And the electric field lines is in this direction. Electric field lines is in this direction. Is in this direction. Just say this direction. This is your area. This is your surface. Area vector is going in this direction, right? And your field is in this direction. Your field lines are touching the surface, going like this. Means parallel to the surface. Area vector is going like this, perpendicular to the surface. Field lines are coming like this. Like this. Is it okay? Yes. Then what will be the electric flux? Yes, EA cos of 90 degree. So you get yes, EA dot into 0. So, is it okay? Good. If you understand, it's very interesting. Okay. If you study according to the book, then you will just stop it at once. Now, the next one I will just give you a question to solve. draw a cuboid. Let me draw a large cuboid so that in the video it will be visible. Let this cuboid lie on this coordinate frame. No? Right? X, Y, Z. This is the origin. Okay, let's say that electric field is going in this direction. Your electric field lines is in this direction. Okay? Your electric field lines is in this direction. That's okay? It's going in this direction. Just that direction. Don't draw. Just say that. Alright? Can you find out the electric flux on all the 6 faces of this closed surface? And the net flux on the entire cuboid. Is it okay? So see, you have to find out the electric flux on the entire, on all the surface of this cuboid. This cuboid has 6 faces. So you will have 6 surfaces. So I want you to find out the electric flux on all of those 6 surfaces. And also the net electric flux through this entire cuboid. Okay? How many faces? 6 faces. You can find out the electric flux through the phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. You have to find all those. And then your resultant, your net electric flux through this entire cube, throughout this cube, will be given by scalar quantity, do not. So just simply algebraic addition, right? Up to 5, 6. That gives you the net electric flux through this entire closed surface. Okay? Good. Now, you see, in order to calculate the electric flux on each surface of this, okay, closed surface, on each face of this closed surface, you see, shall I take this as your surface 1? The top face, let it be your surface 1, right? What will be the direction of the area for this surface 1? Towards J cap. So your area vector is in this direction, right? Your area vector is in this direction, so they are perpendicular. So angle will be 90 degree. So phi 1 will be 0, right? Now let me take the bottom face. Top face means your face 1, bottom face is 2. For this face 2, the area vector will be acting perpendicularly outwards like this. Electric field is in this direction, right? What will be the angle between them? 90 degree. That means phi 2 is also 0, right? Let me take this face as 3, this face as your third face. Is it okay? The area vector, the area will be pointing in this direction. Electric field is also in the same direction, right? So in that case, angle will be 0 degree, right? So phi 3 will be only E cos of 0 degree, E. What will be for phase 4? Phase 4, the area will be in this direction. Electric field is in this direction, okay? Both they are going away from each other. That means angle will be 180 degree. Cos of 180 degree is -1. So this will be minus EA, correct? What about for a front face? This cuboid has one front face, right? If this is the front face, then area will be acting in this direction. Electric field is acting, area in this direction, electric field in this direction. Angle between them will be 90 degrees. So phi 5 is 0. Similarly, there is one surface on the back opposite to the front, right? For that, electric flux is also 0. So the net electric flux will be given by, it's a scalar quantity, so we don't do vector addition, okay? We just simply do phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6. That's 0 plus 0 plus EA minus EA. I mean, mobile games EA ko gina biya sila. Yes, EA means what? Huh? Electronic arts. Okay. That's it. Is it okay? So, are you getting this? No? Okay, alright. Then I have a question for you. I have a question, a very good question for you.
Actually, I also got minus E now.
Okay.
By the way, angle B from 0 degree.
Okay. Oh, no, you use the direction. No, I minus I that is all. No, that is not correct. Angle, electric field is in this direction. Area vector is in this direction. Angle cannot be 0, 180, okay? But direction-wise, so if you write minus I cap, it's correct. But while finding the flask, you need to write the angle also. No? So the next question. Suppose if an electric field is given by, E equals to 6I cap plus 4J cap plus 3K cap. Is that okay? Electric field is given by this direction. Find the electric flux through a surface of area 20 units, okay, in YZ plane. Electric field is given, okay, in vector notation. You want to find the electric flux, okay, over a surface of given area, 20 square units, okay, 20 square units, and your surface lies in YZ plane. So can you find out what is the electric flux over that surface? So, an electric field is given. Your electric field is given to be 6I cap plus 4J cap plus 3K cap. Now, your surface has an area of 20 units, okay, and the surface is placed in YZ plane. So your area vector will be 20 I cap. 20 I cap, because, okay, the area will be directed in a direction, will be in a direction perpendicular to XY plane. That means along the x-axis. X-axis is represented, the direction of x-axis is represented by I cap, right? Therefore, your electric flux will be, okay, E dot A. Your E is 6I cap plus 4J cap plus 3K cap, right? Dot. cap. I dot I is 1. So 6 into 20 is 120 I. J dot I is 0. K dot I is 0. Alright? So 120. Yeah. Yeah, correct. I dot I is 1. Okay. I'm writing still I. Alright. Now we are coming towards the Gauss theorem. Actually, it's Gauss law. It's Gauss law. And for law, no proof is required. Is it okay? In the book, they gave it as theorem. It should be Gauss law. Law do proof neither. Right? When we state and proof Gauss law, we'll be looking at the Q. Let's see. Consider a closed surface, 3D surface. Consider a closed surface, okay, enclosing a charge Q. Enclosing a charge Q at its center. Okay. Consider a sphere, okay, and this sphere encloses a charge Q. That means a charge Q is situated at its center. Let P be a point on the surface of this sphere, okay? Then what will be the direction of the electric field at this point P? What will be the direction of the electric field at this point P? Quickly. OP da. OP equilibrium to the radius of the. Yeah. Electric field at this point P will act radially outwards. Okay, will act radially outwards. Electric field due to a positive charge acts radially outwards, right? Yes. And what will be the okay. And what will be the what do we call okay, what I'm going to do, okay, so electric field at the point P, right? Now electric field at point P will be given by what? Electric field at point P will be given by, what is the electric field at any point due to a charge? 1 by 4 pi epsilon naught into Q by R square, square of the distance. Shall we take, let R be the radius of the sphere? Okay, and if P is a point on the surface of the sphere, then the distance is R, right? So Q upon R square. You can always mention the direction. That small r cap be a unit vector representing the direction of E, right? Okay. Or it's alright if you write only magnitude also for now. Okay, you can consider only magnitude. Okay. Alright. Consider a small element ds. Consider a small area element ds on the surface of this sphere around the point P. Okay? ds is a small area element around the point P. Is it okay? Then what will be the direction of this area element ds? What will be the direction of the area element ds? Towards E only. Is it okay? So the electric flux through this small area element ds will be given by, see, the area element ds is infinitesimally small, so it will have infinitesimally small electric flux, so it will be given by E dot ds, okay, yes, so it will be E ds cos of 0 degree. E and ds are in the same direction, so the angle between them will be 0 degree. So that is only E. Yes. Is it okay? Can we consider that the entire surface of this sphere is made up of a large number of this ds? Right? So we need to find out the electric flux for all these small area elements ds. Right? So another d phi will be E ds. For this area element also d phi will be E ds. For this area element also d phi will be E ds. For this area element also d phi will be E ds. Is it okay? So your total electric flux through the entire surface of the sphere will be given by, can be obtained by adding all this d phi, right? All this d phi, a large number of d phi, uncountable number of d phi. And d phi means what? EDS, right? Plus EDS, plus EDS. Okay? Taking, is it all right? Then in that case, instead of that, what I can do is, because I cannot keep on adding them up, it extends up to infinity here. So instead of that, I can integrate this d phi. Adding all this small d phi means integrating d phi. Is it okay? Closed surface, no? Alright? So, integration of d phi. What is your d phi? E ds. Can I take out E and write ds? If we add all this small ds throughout the surface of this sphere, then what will it give you? If you add all these area elements around the sphere, around the surface of the sphere, then what will it give you? Sum of all these ds will give you the area of the sphere, right? And the area of the sphere, okay, electric field, what is your electric field? 1 by 4 pi epsilon naught into Q upon R square. Into what is your surface of the sphere? 4 pi R square. 4 pi R square Q upon epsilon naught. This way. So this can be rewritten as 1 upon epsilon naught times Q. So the electric flux through any closed surface enclosing a charge is given by 1 upon epsilon naught times the charge enclosed. So Gauss told us, why are you doing all this? Why are we doing all this? This is mathematics. We don't need mathematics here. He only said that if there is any closed surface enclosing a charge, then the electric flux will be given by like this one, simply. No need of doing all this. Is it okay? Yes. So whenever you see any closed surface enclosing a charge, and if you want to find out the electric flux, then this is what we use Gauss law. The total electric flux through any closed surface enclosing a charge is 1 by epsilon naught times the charge enclosed. Are you getting me? So this is how we prove Gauss theorem. So state and prove Gauss theorem. Yeah. Gauss theorem says that the total electric flux through any closed surface enclosing a charge is 1 by epsilon naught times the charge enclosed. And this is how we prove. Is it okay? Yes. Can you prove it? All right. So Gauss theorem says that the total electric flux through any closed surface enclosing a charge is 1 by epsilon naught times the charge enclosed by the sphere. And also we have seen that the electric flux through any closed surface is given by integration of E dot ds. So comparing equation 1 and 2, we have integration of E dot ds is equal to Q upon epsilon naught. We have to keep this relation, okay, in our mind. So Gauss theorem says that integration of E dot ds is equal to Q upon epsilon naught. Okay. Now I want to prove Coulomb's law from Gauss law. Using Gauss law, I want to prove Coulomb's law. What was your Coulomb's law? Coulomb's law says that the force of attraction, we cannot say one by like that, okay? You have to say force. Now, the force of attraction or repulsion between any two charges is given by 1 by 4 pi epsilon naught into product of the charges upon the square of the distance between them, right? Okay, so this is what we want to prove using Gauss theorem. So what I'm going to do is I'm going to consider a sphere. I'm going to consider a sphere enclosing a charge Q at its center, right? Okay, Q1 at its center. Let P be a point at a distance r from the center of the sphere, and I'm going to place another charge Q2 at that point P. Okay? Now, what will be the, according to the electric field, what will be the force exerted on Q2 due to Q1? What will be the force that will be exerted on Q2 due to Q1? See, electric field is defined as force experienced per unit charge, right? Is it okay? Yes. So that means F is equal to Q times E. Is it all right? Yes. So basing on this, what will be the force experienced by this charge Q2 due to this charge Q1? Force experience will be given by Q2 times E. This charge is experiencing a force, so the electric field is given by force experienced per unit test charge. Here your test charge can be assumed to be Q2, right? So in that case, F will be equal to Q2 times E. Now, if you consider a small area element of the sphere at this point P, then its area vector will be directed in this way, right? We'll be acting in this direction, no? Area will be perpendicular to the surface. Is it okay? And it should be joining the center, right? And what will be the electric field? What will be the direction of the electric field at this point due to this charge? It will act radially outwards, right? Is it okay? Yes. So the electric flux through this small area element, just say that this element has an area ds. So the electric field through the small area element ds is given by d phi. D phi is equal to what? E dot ds, right? E dot ds, correct? Now, so your E dot ds. E dot ds means E ds with the cos of the angle between them, 0 degree. So that is simply E ds, right? Now, so the total electric flux over the entire surface of the sphere phi will be given by what? Surface integration of E ds. So that is equal to E integration of ds. Is it correct? So that means phi will be equal to E times, what is ds? 4 pi r square integration of ds. You add up all this ds, then it gives you the area of the sphere, 4 pi r square, correct? Correct? Now according to Gauss law means what? The total electric flux through a closed surface enclosing a charge is given by 1 by 4 pi, or 1 by epsilon naught times the charge enclosed. Here the charge enclosed by the sphere is Q1, correct? Is equal to E times 4 pi r square. From here, if you find E, then your E will be 1 upon 4 pi epsilon naught, into Q1 upon r square. Is it alright? Suppose this is equation 1, this is your equation 2. Okay? Then from equation 1 and 2, what do we have? F is equal to Q2 times E. Q2 times E. Your E is 1 by 4 pi epsilon naught into Q1 upon r square. So that's 1 by 4 pi epsilon naught into Q1 Q2 upon r square, which proves the Coulomb's law in electrostatics. Okay, so define Gauss law or define Gauss theorem, deduce Coulomb's law from Gauss. Is it okay? Question can be asked.
Sure.
Yeah.
This one is the applications of course.
Oh no, not this.
No.
Here.
Applications of Gauss theorem. The first one, electric field due to an, I have not discussed limitations of Gauss law. Okay. So electric field due to an infinite line charge. Electric field due to an infinite line charge. In physics, no? 3D surface is called what? Closed surface, and that closed surface is also called Gaussian surface. Gaussian. Okay, Gaussian surface. Some say Gaussian surface, depending on the region or territory, no? Or depending on the country where they stay. Gaussian. All our teachers say it was Gaussian. But I think it's Gaussian. It's alright, whatever it is, if we can do it correctly, then it matters. No one will deduct marks for saying Gaussian or Gaussian. So consider a infinitely long thin line charge. Infinitely long. Okay? Having positive charge. Is it okay? Uniformly distributed along its length. Is it alright? Yes. Now, I want to find out the electric field at any point P, okay, due to this line charge. Alright. Now, the electric field at this point P due to this charge will be what? Will be in what direction? The electric field at this point P due to this charge will act radially outwards, right? Is it okay? Yes. So it will act radially outwards. So electric field acts radially outwards. Let R be the distance of the point P from the center of this line charge, say O. Is it okay? Now, in order to determine the electric field at this point P, due to this line charge, what do we need to do? We need to draw a Gaussian surface, or a closed surface through this point P. Okay? And that surface should enclose this line charge at its center. Is it okay? See, there are a few limitations, okay? Very important. Limitations of Gauss law. Limitations of Gauss law. Or, Gauss law is always applicable but not helpful. Is applicable but always not helpful. Give reason. Number one, the Gaussian surface should be symmetrical. Itu problem asini. Should be symmetrical about the given charge. To the given charge or about the given charge. About the charge that it is enclosing, no? The Gaussian surface should be symmetric about the given charge. Are you getting that point? Should be symmetrical about the given charge. Number two, okay, at every point on the surface, the charge should be equally distributed. At every point on the surface, on that Gaussian surface, the charge should be symmetrical. Okay? The charge should be symmetrical. The charge should be symmetrical on the surface. This is the second point. First point, the Gaussian surface should be symmetric about the given charge. Second point, the charge should be symmetrical on the surface. The third point, the Gaussian surface should not pass through any charge. Should not pass through any charge, any other charge. Should not pass through any charge. Your surface should not pass through any charge, but the charge should be enclosed at its center. These are the limitations. Is it okay? Yes.
That is why we took the charge in the sphere.
Yes. For that reason, here also I have to draw a Gaussian surface in such a way that the charge will be symmetric about the surface and the surface will be symmetric about the given charge. Is it okay? For that, I have to draw. So what kind of Gaussian surface will I draw here? That is very important. So that the charge will be symmetric about its surface. Okay? And the Gaussian surface will be symmetric about the given charge. Yes. So the only Gaussian surface is to draw a cylinder through this point P of radius r. Okay? So let's draw a Gaussian surface through this point P of radius r. Alright? Now, the total electric flux through this surface will be sum of this surface, sum of this curved surface, and sum of this surface. The sum of the electric flux on this surface, over this surface, and over this surface will give you the total electric flux through this entire surface. Okay? The resultant electric field, the net electric flux over this surface will be given by sum of electric flux through this area of cross section, sum of electric flux through this area of cross section, and the sum of electric flux through this curved surface area. Alright? So I'm going to calculate that. I'm going to calculate koribo. Okay. Now see, consider what will be the what will be the direction of the electric field over this area of cross section of the cylinder. Electric field lines laga direction do kati hobo? No. Area vector. Ito laga area vector do? It will be directed radially upwards, perpendicularly upwards, right? It will be directed perpendicularly upwards. No? And the electric field